cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
That's right, we're back for Season 2 here on Whimsical Wavelengths. Back for Supermassive Black Holes, an episode with enough gravitational pull, you can't help but be sucked in. Clearly, as a geophysicist, not in my wheelhouse, so I'm thankful there's a guest coming on to probe the darkness. I believe this episode will be playing with some ideas that were partially covered in previous episodes from Season 1. Yes, there's a back catalog of evergreen information just waiting for you. Gravitational lensing with Dr. Yorgos Vernados, and simulating dwarf galaxies with Dr. Eric Anderson. Perhaps let's start this episode off with, what is a black hole? Well, it's a solution to Einstein's theory of general relativity, where mass is compressed into such a small volume that it mathematically creates a region of space-time with infinite curvature, a singularity. A point of infinite mass and zero volume. There's an important point here. The singularity is a mathematical construct. In the natural world, there is no infinity. When one shows up through scientific theory, it shows that the theory is too simple to handle the extreme cases. In this case, it's important to point out that a limit towards infinity is not the same as infinity, at least for all my math nerds out there. So perhaps it's safe to summarize this early deviation as a black hole is a region that has enough mass concentrated in a small volume where anything caught in its gravitational well cannot escape. That boundary, when something crosses that line where it can't escape, there is no escape, is called the event horizon. Short deviation, as a kid, that movie terrified me for some reason. I have no idea. One of these days I should watch it again, and I bet it will be terrible in the sense that it's just a bad movie and not scary at all. What is scary is when I tried to tell a joke near a black hole's event horizon. The punchline got spaghettified beyond recognition, and all I got was the silence of the void. So how do black holes form? At least the stellar mass ones from stars. I like to think of it as like this. When there's enough matter gathers in one spot, it's essentially a battle with gravity. In a star, fusion pushes outwards, balancing gravity. But in massive stars, once fusion runs out of fuel, nuance with regards to iron, gravity wins. The star collapses in a supernova, leaving behind a dense core. A gravitational well so deep that not even light can escape. So perhaps you've seen recent news of supermassive black holes in the center of galaxies, those first images, and the one most recently created via AI machine learning algorithms from the same set of data. Supermassive black holes are also absolutely integral to understanding galaxy evolution, because we need to understand what's at the gravitational center, how they grow and interact with their surroundings. To investigate those and go deeper, we need someone other than me. Strap in as we spiral into the dark heart of galaxies, where black holes aren't just sucking up gas and dust, they're gravitationally irresistible. From spaghettified facts to the hottest gossip circling in accretionary disks, it's time to welcome the guest of this episode.
Please welcome to Whimsical Wavelengths, Dr. James Chan, a postdoctoral researcher at the American Museum of Natural History and City University of New York.
Thank you, Jeff, for having me here. It's a great pleasure to share my knowledge and my research with you guys.
Thanks a lot for being here. So to get to the bottom of what we're going to be talking and discussing here and investigating as the paper at the center of this episode, we need to start at the top. So broadly, what is your research questions that you're trying to answer? And or what are you investigating in a broad sense?
For me, I would like to answer everything about the universe. Yeah, so
that's super broad. Everything, like I think Hitchhiker's Guide to the Galaxy did that, didn't he? Like the answer is 42.
Exactly. Yeah. So I think the final answer is 42. No. Of course, we want to understand how the universe formed and how it evolved and what's the future. And the tool that currently our group try to build up the tool combining with the gravitational lensing and also the machine learning techniques. And then our target source is something called AGN.
The Active Galactic Nuclei. this seems like really, 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 really broad instead of very narrow. So are you using the, because we've had a couple of episodes on using gravitational lensing to understand different parts and look beyond what's in front of it. So using it as a lens, are you trying to peer further back into the universe, or are you trying to use gravitational lensing to tell you something about the source?
Exactly. So gravitational lensing can magnify the background source. So like most of the AGN, they are far away from us. So using gravitational lensing, we can see the source far away and also the very tiny inner structure.
So you're trying to look at the active galactic nucleuses of galaxies billions of light years from us instead of our quote unquote galactic neighbors.
I would say both, because if we want to study the galaxy far away from us, we need to understand the galaxy close to us first. Yeah. So it's just a tool. So if we want to study the evolution of the AGN, for example, and then we need to use lensing. That's why lensing come into play.
Okay. Just for those that followed around in season 1, the lensing, you're using the lens created by the supermassive black holes and the active galactic nuclei to tell us something about the nuclei itself?
That's a very good question. So in fact, no, the AGN, the active galactic nuclei, is a source. And the lens itself is a foreground galaxy. It's a massive galaxy.
Right. What I mean is, though, we had Yorgos Bernados on the podcast in season 1, and he was explaining how you can essentially, very much like in my own particular field with geophysics, observations of the lens, you can use that information to invert about things like mass distribution and the like of the source.
Exactly. You can do that. And you can, at the same time, you can also study the structure of the source. Right.
So my question is, are you generally, not always, but generally, not talking about physics in the grand scheme of things, and because there's a million different ways to look at different things, but within your own research, are you generally looking at the source, or are you looking at the things through the lens?
Oh, that's a very good question. I think it depends on the group I join. So me personally, I want to understand everything, as I said. I also want to study the structure of the lensing galaxy. But currently, our group here, we try to focus on the source, the AGN itself. So that's why we want to study the structure nearby the supermassive black hole in the active galactic nuclei.
Right. Okay. And so that's generally the tack that the paper we're going to be talking about here.
Exactly. Yeah. But
okay. But your research is much broader than that. Got it. You want to look at the whole system. You're a big picture person. And sometimes to understand the big picture, we got to get down into the details of something specific, like one specific source. But generally, your interest is much broader than that.
Exactly. Correct.
Awesome. Okay. So the paper we're chatting about here today is, I'm going to do my best to say it all in a perfectly understandable way, Reverberation Mapping of Lamppost and Wind Structures in Accretionary Thin Disks, or Accretion Thin Disk. For those without background, me included, at least at the beginning before I started to research a bit more to episode to make sure I can ask coherent questions, it's basically incomprehensible at first read. Yes, they're English words, but it doesn't make a whole lot of sense at the beginning. But I think we can get there. And I think we've already kind of got this ball rolling with the first 3 words of the paper of active galactic nuclei, which is where a black hole is actively eating stuff. Is that right?
Correct.
Okay,
Correct.
So then the next question would be, are there inactive ones? And then what is an inactive one if it's a black hole? Like black holes are always eating things, aren't they?
That's correct. So let's talk about an inactive one. So for example, our Milky Way is not the active. There's no active galactic nuclei. The center of our Milky Way is a bit, we say, quiet. Yeah. So since it's not that active, so the center is not that bright.
So that just means that it's not eating things?
It's still eating, but slowly. It's not like active one. So
Okay,
usually,
just really random question. So is there like a certain emission rate or luminosity index that you would apply to the center of galaxies to determine if they're inactive or active?
oh, okay. So maybe we can come with the question is, what if the Milky Way there's an active galactic nuclei? What happened of our Milky Way? Do you want to guess?
I have no idea.
So if it's active galactic nuclei is an AGN, then our Milky Way center will be super bright. Yeah. So when I say super bright, it's still not as bright as our sun because our sun is very close to us. Yeah. But it would be very bright and it may change the structure of the inner galaxy.
So you're saying you would be able to see the center if you were on the part of the Earth pointed towards it, you'd be able to see it at night.
Exactly. So for example, now if you look at the galactic center, we have the picture of our black hole from the event horizon telescope. But if you look at sky, you cannot see anything. You need a very, very powerful telescope to see it. But if this is an AGN, we can see the light coming from the center.
Okay.
Yeah. And maybe I should have the question is, do you think the life on Earth can still survive? I think that's a question, more interesting question, right? If the Milky Way there's an AGN.
Wow. Like that's actually a question. It's how many light years away is the center of the Milky Way?
I think it will be 23,000 years.
And so
I don't remember. I need to double check.
But the point is it's in the thousands, right? It's in the thousands. So even at that distance, there would be enough radiation reaching Earth that we would feel the effects of it.
Correct. So I think based on my estimation, I checked it yesterday. So I think we are still fine because we are far, but we will see like something like star, even though it's not star, shining at the center of galaxy.
Wow.
Yeah.
That's crazy. So we don't have one, and that's good.
Mm-hmm.
At least for other possible life forms in our galaxy, should they exist. And also, one more thing. Active galactic nuclei suggests that there could be more than one within a single galaxy, right? Before we move on?
Oh, that's also a very good question. So generally, there's only one supermassive black hole in a galaxy at the center. Yeah, usually. I would say probably more than 90% galaxies has only one supermassive black hole. But if there's a galaxy merger, for example, in the early universe, then you may find like double supermassive black hole, but that's quite rare, I would say.
So in the intro, I gave a quick little introduction to roughly how your stellar mass, your garden variety black hole might form. But the best I've seen for like understanding supermassive black holes is that like they formed in the early part of the universe just under direct gravitational collapse ? So like how should we understand the formation of supermassive black holes? Like it's not something that's ever really talked about in a straightforward manner. Is it because we just don't know?
Yeah, Jeff, this is a very, very good question. So the short answer is I don't think we really know how the supermassive black hole really formed. But yes, for the stellar mass black hole, for example, the mass is around 3 to 30 solar mass. For this kind of black hole, they are coming from the star, the dying star, the very massive star. But to form a supermassive black hole, currently we have two scenarios. One is this kind of the massive black hole, like stellar mass black hole, form in the early universe, and then they merge with others, and they merge until we form the supermassive one. Yeah. So imagine if you want to have the black hole from, let's say, 10 solar mass to like a million to billion solar mass. That takes time. And I think we need to find them at least on the sky so that we can confirm this scenario is correct. So currently, we're still missing a lot of, we say, intermediate black hole, which is the mass around like 1,000 or 100,000, this kind of mass range. I don't think we really find it. So from the observation, we miss the gap of the stellar mass black hole and the supermassive black hole. But there's something very exciting is last week. So people found the most massive black hole merger from the LIGO. And this black hole merger, the total mass is around like, I think 200 solar mass. But this is so far the most massive we can find. Yeah, this is already from 30 something to like 200. So we have some progress, but still there we need to find more to confirm this scenario. So this is one possibility. Yeah, another possibility is people propose maybe this kind of supermassive black hole, they form from the gas cloud. So maybe there's a giant gas cloud somewhere and they can just collapse and form a black hole around like 10,000 or 100,000 solar mass. Yeah, so this is called a direct collapse black hole. Yeah, but I don't think we really found one yet. Yeah, so this
right,
scenario,
I think my understanding is the evidence for that is more to the fact that no matter how far back we look, we keep finding these supermassive black holes.
Yeah.
And so we're left with, okay, how do we get them? So I think that's kind of where it came from, this idea, right? That they could come directly from. Okay.
Yeah, but so far I don't think we really know the answer.
Right. The paper here is modeling the accretionary disk of supermassive black holes. And is that just how it sounds? Accretionary disk, meaning material collected by nearby sources that assumably also spins to create it being a disk?
Yes, exactly. Yeah.
So it is exactly how it sounds. It's like it's almost like the way we are taught that the solar system formed through a spinning cloud of gas that formed a disk, and the same idea, but at a grander scale, if you will.
All right, we just scaled it from the small like sun to the galaxy.
Okay, so it's fair to say that in these active galactic nuclei from these singular supermassive black holes, that they grow by incorporating material that falls into them from this disk generally?
Correct. Yeah.
Okay. Well, I've learned not to take things to assume too much, because oftentimes they're completely wrong. Also, light. I mean, it's a black hole. So light goes into the black hole and doesn't really come out. So how do we observe how do we observe what we observe? If these disks are something we can easily observe, why is that light from these disks not just going down into the black hole?
Wow, that's also an excellent question. So currently we only have two pictures of black hole, right? With Event Horizon Telescope. And
well, if we include the AI, that would be 3, right?
Yeah, but that's not real. It's emulated. Yeah. So the Event Horizon Telescope basically is a telescope like as the size of our Earth. Yeah. So this powerful telescope, we can see the black hole picture. But if you want to observe the black hole, supermassive black hole far away from us, is I don't think it's possible. Yeah. So the way we try to do that is because accretion disk, there's a light coming from the accretion disk. So we see how the galaxy or AGN change the light, the brightness. Based on that, we can infer the model. We infer the structure based on the model. So, and then we can say, okay, so if the model is like this is how the brightness would change. And if it match the observation, then we can say, okay, the model is correct.
Okay, so let me see if I understand this correctly. You're optically observing these from a distance. You have their whimsical wavelengths, if you will. Yeah. And based on the radiation and the wavelengths you've recorded, you fit it to physical models that reproduce the physics as we understand them to determine what's going on there.
Exactly. Yeah.
So that kind of brings me right into the next part, because I guess when it comes, it's in the title of the paper as well, winds. On Earth, it's the atmosphere moving to the differences in pressure. The solar wind, if you will, is charged particles released from the sun. You can even say that they create a pressure of themselves when they push on things and create certain the dividing line between interstellar space, for instance, is the difference between where our solar wind no longer has any effect. So, but black holes have wind? Is it just based on the physics? Is it because I thought they're supposed to suck everything to their center? So how are they creating wind? Especially because we're not exactly observing it, right?
Yeah, that's an excellent question. So, in fact, they are not exactly the same, but the mechanism is also quite similar. So on our Earth, we can have the wind based on the temperature gradient, right? And then for the sun, we have solar wind, and that's based on the also temperature gradient and also I think magnetic field. So for the black hole winds, it's also driven by the temperature gradient and also the magnetic field around the black holes and also around the accretion disk. So you can imagine the accretion disk, there's a temperature gradient. So the hotter at center and the cooler in the edge. So there's a wind push the material from inside to outside. Yeah. And also, of course, there's another pressure. It's called radiation pressure. Yeah. And also sometimes there is a jet coming from the AGN that can also push the material from inside to outside. That's why we say these are black hole winds.
How do we observe? Is it the wind is something that comes out of the physics directly, or is it something we can directly observe?
Oh, it's hard to observe. So, and we don't even really understand how this wind mechanism works. So my works currently, I try to incorporate different wind models in the accretion disk.
So you're saying we know it must be there because of the nature of what's going on, but we don't necessarily understand all the details and mechanisms, nor can we observe those details and mechanisms.
Oh, I would say this is one of the mechanisms that possibly to resolve the discrepancy between the traditional model, and the observation. So maybe
okay, I see it. So in other words, we know accretional disks, we have direct observations that those exist, and models that don't take into account these other effects fail to reproduce the data. And so one way to help reproduce the data is to use wind, quote unquote, to help get the model to the point where it can reproduce the data.
Exactly. So that is one mechanism we can play with to add into our model.
Right. And that's driven by temperature and radiation.
Exactly.
And do we have any ways to observe what the radiation is from these?
So one possibility is we can observe the nearby AGN and see if our model can really match the observation. But to really observe the wind, I don't know.
Not yet, eh?
Yeah, not yet. I don't think so.
That's fair. Earlier, you mentioned that there was a question whether or not life on Earth could exist if we had an active galactic nuclei.
Mm-hmm.
So the wind, the radiative pressure, all of this stuff, this must travel a long way out from the center, much beyond the disk itself.
Yes.
So we're talking thousands of light years away.
Exactly. Yeah.
That's mind-blowing. Thousands of light years. So that's, I guess, the radiation that we would be most worried about is really hurt us here on Earth. And I would assume it's a similar process,
to the solar wind.
Quite similar. I would say it's quite similar. Yeah.
Yeah, it's crazy. Thousands of light years. Anyway, all right. So disks, EM fields, it's a black hole. So gravity, their effects cover thousands of light years. These massive behemoths at the center of how much do they actually control as far as the evolution of a galaxy? Is it the whole thing? It's the seed that everything's built off of?
So when the galaxy, the center is active, then they can trigger a lot of mechanisms. For example, the radiation will become stronger, and stronger radiation can, for example, shut down the formation, the star formation. in the galaxy. So if the galaxy is very active, you may not see so many stars around the center. Yeah, this is something we call the AGN feedback. Yeah, and this mechanism, in fact, is very important because, for example, like previous episode, you have the Eric, and then so he's interested in simulating the galaxies. So he has to put the realistic physics into the simulation. So if he doesn't put, for example, this AGN mechanism into his simulation, then the galaxy will become unrealistic. Yeah, and you cannot use it to compare with the universe, the data, for example.
Okay. And so I guess accretionary disks are then very important to the whole evolution of that galaxy as well, right?
Yes. To understand the evolution and what's the real structure, what is a wind model in the accretion disk is very important.
Right. So would accretionary disk models also affect that, if I remember correctly from what Eric was describing, Dr. Eric Anderson, he was saying there's a certain temperature at which you need to get below so gravity can start to win, so you can get towards concentrating enough stuff to actually start star formation. So I guess the models around that wind and radiation around the accretionary disk are quite important to understanding that process too, then, right?
Exactly. Yeah.
So in other words, your own study here, or the implications of it in the future, might go into his future galaxy models.
Yes, because currently the paper you pointed out, we use a kind of semi-analytical model. It's still not a full simulation. Yeah, and to have this kind of full simulation is very expensive. Yeah, so in the future, of course, we want to have a full simulation, and I think that would be ideal, but it's still a long way to go.
Well, that's like the perfect segue, because now it's time to get some more technical details, and we're getting closer to being able to understand the actual title of the paper itself. So, to quote the paper, focusing on a geometrically thin and optically thick disk, model irradiated by an external lamppost source. I think this is a statement of the assumptions of the method.
Correct.
Okay, good.
Yeah.
So which part is the assumptions?
So geometrical thing, you can imagine that this is like pancake, super thin. And then I honestly, we choose that. One of the reason is because it's easy to model.
Okay, so it's basically saying you can ignore the geometrical thickness of it. We can treat it as just a plane.
Exactly, because it's really tiny in the center. So I think this assumption, I wouldn't say is a best one, but it's a okay one to use. And because
especially at the scale and resolution that we're dealing
with. Exactly.
Okay, but how do you match that with the idea that it's optically thick?
So optical thick, it means the photon will be absorbed immediately from the disk to the disk. Yeah, and the photon would reprocess and emit again from the disk. So the photon coming from then goes to the lamppost, the center, can be absorbed and reprocessed directly. There's nothing he will lose. That's why we use this kind of optically thick. So it's also easy to model, I would say.
So does that mean in the model or whatever, that the photon can never escape?
The photon cannot, exactly, yeah.
Okay. So that's the assumption here, because obviously photons escape because otherwise we wouldn't see them as bright areas, right?
Yeah, exactly, yeah. So imagine if you have a milk, and you basically cannot see through the milk because all the photon would absorb by the milk. But if you have water, the photon can go through. Yeah.
Okay. So that's obviously they're not perfect assumptions because there's something to be left behind, but it gives the ability to start to look at some of the processes like the wind, I'm assuming.
Exactly. Yeah. It's a simple model, but I think so far it's still fine to use. But I would say we can do better.
Yeah, but again, it comes down to how many years do you want to wait for the code to run sometimes too, right?
Exactly, correct.
Okay, so now for the last part, so we can actually understand each part of this title, reverberation mapping.
Oh.
In truth, this is where my understanding of reading the paper begins to completely break down, because reverberation in every day essentially means echoes, sound waves bouncing off of surfaces. So my best guess, because I wasn't able to find a simple definition of it, is the technique is observing the radiation bouncing through the disk to calculate the parameters of the black hole.
I think you're getting there. You're right. Is like what you said. Yeah. So maybe I can go into a little bit deeper about this kind of reverb.
Please do.
Yeah. So the difference, we know there's an echo and the reverberation mapping. So the echo is, I think, is a clear difference between the reflection of the sound. Right. So say hello. And a few seconds, you can hear hello. That's echo.
Things are going to change, like the wavelength, the amplitude, etc.
Yeah. But for the reverberation mapping, or I think in the acoustic term, they just call it reverb. It's a series of the reflection of the echoes. So you cannot see the difference. What you can hear is like I don't know. Imagine if you're in a huge room. When you say hello, something like this. So in fact, I have the audio. If you want, I can play for you. I don't know, that would be useful for the.
Sure, let's give it a try.
So this is a normal sound.
Go.
Yeah.
Play it again.
Yeah.
Go.
Okay, and now it's an echo.
Go.
Okay, this is the echo.
Go.
Now it's a reverb.
Go.
Oh, I see. Yep.
Yeah. So this is a reverb.
Go.
So this is a reverb.
So the way it's dispersed and reflected at the same time, that there's
exactly.
no...
Too many sounds, like a reflection happening. So you cannot see the distinction. You cannot distinct them. Yeah. And that's also happened in the accretion disk, because we assume the light is coming from the center, the lamppost. So light comes from the center, and then reprocess the disk, and then re-emit again. It's like a reflection, a bit like that, but it's more complicated. But you can imagine like a reflection. But since the disk is a kind of continuous structure, so all the photon would reflect at the same time. That's why we call it reverberation, not the echo. But basically, it's a series of echo. Yeah. So. For the reverberation mapping is we try to use the echo, series echo, the reverb from the disk, and infer the structure of the disk. Imagine if you go into a room, you hear the sound like this reverb, and you can kind of feel what is the shape or the size of the room. Or if you hear the echo, you can kind of estimate how far of the mountain. Does that make sense?
Yeah, and I guess that process and the analysis that you presented in the paper complicates the methods that are typically used by incorporating those other wind dynamics or reverberation. Is that how to read it?
Yeah, so we just add this kind of wind model in the accretion disk so that you can change, for example, the temperature gradient of the disk. Yeah.
Okay, and so the conclusion was, this is a new method, or adding this information is better at what?
I wouldn't say it's really a new model, because this model, the wind model, has been proposed a long time ago. Yeah, but to really apply to the reverberation mapping techniques, I think we are the first one, or I can say we are the first to really understand properly how to use that in our semi-analytical model. So because in our field, the accretion disk size, there's a discrepancy between the measurement and the theory. So from the observation, people mostly observe the disk is larger than we expect. So incorporate with this kind of wind model I wouldn't say can completely solve, but it can mitigate the size overestimation issues.
Okay, so in other words, it's getting it to the point where things are starting to match the standard model, so to speak.
Exactly, yeah.
That's pretty cool. Now, like everything, we stand on the shoulders of giants when it comes to science. So what kind of stepping stone is this to the how is this going to be used in the future? Is it just going to be more detailed models? Is it needing better telescopes? Like, how is this going to be that stepping stone for somebody else to stand on your shoulders?
So I would say first we incorporate with this one WIM model, but we can still refine our model as best as we can. And then, of course, we try to study this kind of echo from the light, but we can also study how bright of this light echoes. So I haven't really applied this model to the amplitude of the echoes. We only try to measure the delay of the echo based on this my analysis. So we can still include the measurement of the brightness or even the spectrum, the spectral structure, spectral features. Yeah. And also, of course, we want more samples. We want more data. So currently in this current paper, we only try to use 4 nearby AGN, and we have the best data of that. But in the future, we should have more data. Yeah.
Nice. Okay, so you've already said that your current or your personal research questions are a lot broader. So for you, looking into the future, not necessarily too far, hopefully, what's the next big thing that you're looking forward to being able to try to probe some of this? Is it a new telescope, new ideas, more data? I don't know, a trip to Mars, interstellar space? Like, what's the next thing that you think will get us a little bit closer to where you want to be, which is life, the universe, the answer to everything?
So for sure, the more data is the key. And currently we have the Rubin telescope. You probably have heard it, the Rubin Observatory. So next 10 years, we will have a lot of data, maybe like a few terabyte or petabyte per day. So using that data, we have to analyze this data very quickly. So there will be a lot of AGN, like probably millions of AGN, and they will provide the change of the brightness very quickly every day. And this kind of the brightness change we call light curves. I should introduce this words called light curves. So we will have a lot of light curves. And how do we analyze the light curve very efficiently? That's another issue because the data is too big. So now the machine will come into play. So we need to train our machine learning model to analyze the data. Yeah. So in order to use machine learning, one of the keys, we want to simulate our light curves in a very general physics. We want to just simulate our light curve with a very tiny physics. That's what we see. Of course, if you simulate that, that's what machine can learn. So we want to simulate something much bigger than our universe. Yeah. And then use a general model, apply with a machine learning, and then compare with observation. Yeah. And more than that, we also have the lensed AGN. So using the gravitational lensing, we can see the inner structure of the AGN. That's also quite valuable.
Okay. So the big thing you're looking forward to is drowning in data.
Exactly. Yeah.
No, that's a good problem to have most of the time, to be fair. There's nothing worse than trying to make up things and you're like, I don't know what I'm doing.
Too many things to do.
Yes. Okay. Well, thanks for being on. Like, it's been great. I've learned so much already, but now I'm about to learn your sense of humor. It's the traditional last question here on Whimsical Wavelengths, the one that I make sure is clearly defined to the guest at every opportunity so that they have the chance to come up with one before they show up in the show. So you get to tell us a science joke.
Okay, so I have a joke about black hole. That's how we talk about today, right? So I have a joke about black hole, but it sucks.
Oh.
Okay, that's the first
perfect.
one.
You've got more than one. You've come prepared.
So this is the story about photon. So the photon, it travel to visit a black hole. So when she arrived, this photon is a female. So when she arrived, the black hole said, "Want me to take your luggage?" And the photon replies, "No thanks. Why?" So this you should know.
Because it was traveling light.
Exactly. Okay. So this is in the previous episode, but this is a follow-up. Okay. So the follow-up is, okay, now because the photon there's no the luggage. So now she catch up with the black hole. So they catch up and the photon just looks closer, look at the black hole, and she says, "Hey, it's been a long time I haven't seen you. And you look like you have lost a lot of weight. What happened?" So the black hole replies, "Yeah, I have been eating light lately."
Oh my goodness.
Okay, that's the last one.
Oh, there's another one.
After that is, because they catch up and the photon, he never made it back home because she's a visiting black hole.
Yeah.
Yeah. So that's it. I hope it's funny.
It's perfect. It's almost better that they're not funny in some respects, because when we're not able to take our own things that we like, I spent from like the age of around grade 4. So what is that? Like 10 years old wanting to study volcanoes. And if I can't, what's the word? If I was in Britain, take the piss out of my own field of study, then perhaps I'm taking it all way too seriously, right?
Of course. Yeah.
So thanks again for being on Whimsical Wavelengths. I'm so glad you could be here. Is there anything you want us to add just before we close up?
So it's really my pleasure. So I hope everyone, your audience, they are all like black hole. They are very attractive and with infinite potential.
Well, that brings an end to episode 3 of season 2. I hope you really enjoyed it. And tune in 2 weeks from now, where I get way over my skis in an interview all about plastic with somebody who studied material science and now is solving problems in industry. It's not my finest work, but I think it's still an interesting discussion, and even if it makes you angry, hopefully I've tied it all in during this end bit, at the end of the next episode. See you in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by.